Hello students, welcome to lecture 5, entitled as Training versus Testing and Theory of Generalization. In the previous lecture, we asked the question related to feasibility of learning. So in particular, we asked if learning is possible, given that our target function is unknown. Can we approximate something unknown? What kind of theoretical guarantees we can give? So we answered to this question using probabilistic approach, in particular utilizing the famous Hofstadter's inequality, and then said learning is probably approximately correct, possible, if enough statistical data and we have finite number of hypotheses. So in this lecture we will continue the previous lecture and then further introduce some interesting definition of effective number of lines, effective number of hypotheses, breakpoints. We briefly talk about the theory of generalization and very important VC dimension. So VC stands for Vapnik-Chervonenkis. Well, let's review the statistical learning flow. What we said is that using the Hofstadter's inequality, if H is finite, H is a set of hypotheses. Okay, if our set of hypotheses is finite, we talked about m number of hypotheses, and data n is large enough, okay, for whatever g picked by algorithm, the E out and E in approximate each other. All right, this was given using the Hofstadter's inequality. This is fine. Well, if A finds one g, let's assume, which is perfect, makes no mistakes, with the in-sample error of that g equal to 0, approximating 0, then probably approximate correct guarantees out-of-sample error to approximate 0 as well, okay, under these two conditions. So m should be, h should be finite, n should be large enough, okay, then the g picked by algorithm A will approximate E out, will approximate E in. So these are the different components again. So what is in-sample error approximate 0 mean? We call these as also train, or the performance of G on training dataset, or we also call them as train error. Okay, how about E out? So E out, G, out of sample error, is obtained on test dataset. So test is future dataset that hasn't been seen, so we don't know about the test dataset. Or we sometimes call this as test error. Out of sample error is usually acquired on test, okay, in sample on train. Now, let me introduce the two important questions in machine learning. So for batch and supervised binary classification that we have covered in lecture 3, and G approximates F. That means our out-of-sample error should be 0, okay? However, this is achieved through, first, making sure that out-of-sample error also approximates in-sample error, which we covered in lecture 4, and in-sample error is 0. Okay, in-sample error is small enough for the chosen hypothesis G. So we can split this into two central questions. First, can we make sure that out-of-sample error for this G is close enough to in-sample error? Second question is, can we make in-sample error of this hypothesis G small enough? Okay, so these two questions will always be around us. So again, one of the important central questions in machine learning is out-of-sample error being close enough to in-sample error. Second is in-sample error is small enough. In ideal case, it should be 0. Now let's delve into the role of the number of hypotheses, which is m. Okay, m number of hypotheses. What role does m play in these two questions? Okay, m is, if you remember, is number of hypotheses in our big H set. To answer our two central questions, there are trade-offs on the number of hypotheses available in our hypothesis set. So to the question 1, can we make sure out of sample error is close enough to in-sample error? We can have two answers. Similarly, can we make in-sample error small enough? So trade-off between large and small number of hypotheses. So if we have limited number of small hypotheses, okay, the answer to the first question could be yes. We can make sure that out of sample error is close enough to in-sample error using the extended version of the Hostings inequality. Why? Because on the right-hand side of the Hostings inequality, the probability of bad event, so bad event again is the difference between out of sample error and in-sample error by some epsilon number, is upper bounded by 2m exponential. So the m, if it is small, yes, so we can make the probability of bad event smaller. Okay, that is equivalent to out of sample is close to in-sample error. So to the second question, can we make in-sample error small enough? If we have small number of hypotheses m, no, because we will have too few choices, okay, in sample. So it will be difficult to find the hypothesis G among the small number of hypotheses available for us. So when we have large number of m, number of hypotheses, okay, the answer to the first question would be no. Why? Because it is the m, because m is big, the probability of bad event will be big, right? And the answer to the second question, can we make sure in sample error small enough, is yes. Why? Because our algorithm has too many choices to select one of the H as G, which will have no mistakes on given the training examples. Right, so here we're talking about the trade-off between small versus large m, and the role of number of hypotheses in answering these two central questions. So using the right m, right number of hypotheses, is very important. And we can also see that if m is unlimited or infinite, okay, we will never be able to answer the question out of sample close in sample, because the probability of bad event will be infinite. So following discussion, so let's take a look at the probability of bad event. This is the extended Hostings inequality from the previous lecture to m different hypotheses. So probability of bad event is equal to this. So this is the bad event. The absolute value of in sample being different from out of sample error greater than epsilon is less or equal to 2m exponential to epsilon squared n. N is the number of examples. Epsilon is some small number which we can call as tolerance. Okay, epsilon is user defined also. And m can be user defined. M is the number of hypotheses, right? So if m is infinite, we're in trouble. Probability of bad event is very big. So now we really want to make sure that m is the good number, right? So we don't want it to be too small or too large. We want it to be somewhere in between. So how can we do that? So our next goal, briefly, will be to establish a finite quantity that replaces m. Is there anything that we can replace m with that will be finite, not infinite, not too big? So here, this is our new form, so probability of bad event to m. So small m, we will try to come up with something that can replace m. As a result, we will avoid potential m being a big set of hypotheses, okay? So, yeah, so justify feasibility learning for infinite m and study what we call small m to understand the trade-off for right hypothesis just like m. So let's take a look at these first and then ask, where did m come from in the first place? So m comes from all bad events, right? This is our bad event again. We extended the single bin experiment to multiple bin and associated with the multiple hypothesis set, so that our algorithm can make some choices. So we said probability of bad event 1, bad event 2, bad event m for m hypothesis, okay? And also consider the worst case scenario where all bad events are non-overlapping. Therefore, we just applied union bound. So probability of bad event 1, B2, Bm is upper bounded by the worst case non-overlapping probability of each event, B1, B2, Bm, right? This is the union bound. And now the question is why union bound can fail, okay? If we consider m to be equal to infinity. One more time, let me clarify. So B1 is this event, right? So for H1. B2 is, again, one of these events for H2, Hm, up to Hm. Let's ask, where did uniform bound fail in the first place? So if you remember, we considered the union bound of all bad events. Probability of B1, B2, Bm. And I just place this table from the previous lecture. What we see here is bad data sample, right? So H1, probability of bad event on this example, okay, H1 being different from the target F, is bad, okay, is upper bounded by the following Hoffe inequality. So we have H1, H2, H3, Hm. We collect all the bad events and then take just the union bound, which is this one. So also, if we consider the Venn diagram of example 3 bad events, we see there are a lot of overlapping region. That means most of the hypotheses in this region will be similar, or they will be equal. Why? Because first, out of sample error for given H1 and H2 will be similar. Second, for most of the data set, the in-sample error of H1 will be equal to in-sample error of H2 and also H3. So we can simply say that the union bound is overestimating, right? So also here, so most H1 will have similar bad events to H2 or H3. For instance, H1, H3 is very similar in this simple table, Hm. All right, so we are just taking the worst case scenario and taking the union bound of all possible probability of bad events. So next important question is, to account for this kind of overlap, can we group similar hypotheses by kind? Okay, so now we talk about grouping similar hypotheses by kind. In order to group similar hypotheses by kind, we'll take some examples. Now, let's consider that our H consists of all lines in R2, two-dimensional vector space. All hypotheses, all lines. And let's draw this R2 and 1 point. How many lines can we use to classify this point into binary classification output? Okay, it could be infinite because we can put all the hypotheses, all the lines here. Okay, that will, or in this side, that will classify, that can provide x1 output as plus or minus 1, or a circle or x1. We can have infinite number of hypotheses. Well, second question, how many kinds of lines if viewed from one input vector? If you view from the eye of the x1, how many kinds of lines or hypotheses we can see that will classify this point into binary output? There are two kinds, H1, H2. For example, here. So we can have H1 that will put x1 in this side and will label it as red cross. H1, which will put x1 in this side and provide us this label. So we can also have this number of hypotheses. Okay, so all is putting labeling x1 as like h1 as this circle, right? Or we can have infinite. So that is what I mean, what we mean. How many lines? It could go infinite, right? So if we group all these hypotheses, that will label x1 as this. We are grouping them by kind. Okay, and also similarly, we can have different hypotheses. Similar to H2 will be located on this side of the point, right? And then we can group all these as H2. All of them label x1 as red, and all of these hypotheses as H1. We are just grouping by kind. Now let's 2 points, x1 and x2. And ask the same question, how many kinds of lines or hypotheses, if viewed from 2 inputs, we can find? All right, so how many kinds, okay, how many different but similar kinds of hypotheses? So, okay, we can think about 4 different cases of labeling. So hypothesis 1 will find it as 2 blues. Hypothesis 2, 2 reds. Hypothesis 3, these different combinations. Hypothesis 4, these different combinations. So let me draw it here, for example. So we can have H1, H2, for example, H3, or H4, right? So we can group all possible hypotheses into one H1 type and H2 type, and all the hypotheses that, okay, lie here as H3 and H4. Here we can see again, so H1 will, identify x1, x2 as 2 blue, and h2, for example, 2 reds. h3 could be here, okay, and identifying it as a blue circle or red cross. And h4 again could be another hypothesis, h4. So again, all the hypotheses that will provide these labels, we're grouping by kind. So if viewed from the eye of the point, for these points, they mean the same one hypothesis, right? Same labels. We can further extend this example to 3-point case. And that same question, how many kinds of hypotheses we can have for 3 different inputs? Is it all lines in R2? Right? So as we can see, it gets a little bit more complicated or extended. So we can have one hypothesis or group of hypotheses that will label them as all blue circles, okay? Or we can have a group of hypotheses that will label them all red points, h1, h2, or we can have all the hypotheses that will label them as 2 blue, 1 cross, okay? Or h4, for example, h5, h6, h7, h8. And in total, we can say that we have 8 different kinds of hypotheses for 3 inputs. But is it always 3 for 3 inputs? No. It depends on the orientation, on the location of the points. For example, if we have collinear inputs oriented in this form, and some of the lines, okay, we're talking about a hypothesis of linear perceptrons, will not be able to provide these kind of labels, okay? These 2 cases, impossible to separate. So in this case, we will have 6 different kinds of hypotheses, okay, for 3 inputs, for this kind of 3 inputs, right? So fewer number than the 8. What does that mean? Is it good news or bad news? If we have our inputs in this form, okay, then some of the hypotheses will not be labeled them into 2 distinct cases because the data is not linearly separable, right? Linear function cannot provide these labels. So we can talk about the effective number of lines or hypotheses in this case, which will be equal to the maximum kinds of hypotheses with respect to n inputs. Okay, we call them as effective number of hypotheses. We're just bringing down the m or infinite or possibly infinite number of hypotheses to only effective number of hypotheses from the eye of the n inputs. So in maximum cases, so we should have 2 to the n number of hypotheses, effective number of hypotheses, as we have seen in the previous examples. So why? Because we're dealing with a binary classification task, or we're expecting binary output values, right? And it is based on finite grouping of infinitely many hypotheses in H. So we are grouping by kind, possibly infinitely many hypotheses in H by kind. For example, in 2D, we have seen the following lines. So lines are linear functions, okay? Also, you can think about them as perceptrons. So when we have 1 point, 1 example in 2D, we have seen the effective number of hypotheses were two. There were just two hypotheses by kind that can label one point into two different labels: blue circle, red cross. When we have seen two examples, 2 points in 2D, we have seen that there are 4 different kinds of hypotheses we can get. 3 examples, okay, when we didn't have collinear examples, we have seen 8 different hypotheses by kind. How about 4? In 4 cases, 4-point cases, we will have 14 hypotheses grouped by kind, which will be less than 2 to the n. 2 to the n, okay, 4-point would be 16 hypotheses by kind. So let me just go back and to demonstrate, to show this example. Okay, so here, so 4 points, x1, x2, x3, and x4. Why 14, not 16? So we will have 2 cases like this, similar to nonlinear separable data. So we cannot provide these labels in 2 cases. Okay? So first 2 blues, 2 reds, and then next possible combination is this will be blue, blue, red, red. And then these are all possible labelings. And 2 times, okay, because we flip the signs, we flip the labels. So we will have 2 cases. We will have 2 cases where the lines will not be able to provide these kind of labels. That's why we see that as we increase the number of examples, we will have less effective number of hypotheses in 2D, and we're talking about linear functions or perceptrons. Okay? So why do we care about the effective number of hypotheses? So initially we wanted to come up with something that will replace our M, right? In original Hoeffding inequality we had M, total number of hypotheses. And we said, what happens if M is infinite? So we want to avoid that situation where M could be infinite or very huge number, or also we want to avoid it to be very small, because we want to answer those 2 questions in mind, of interest. So now, can we replace effective number of hypotheses with the M? Or we can replace M with this effective number hypothesis in the Hoeffding's inequality that we have considered. So if first effective number of hypotheses can replace M, and then second, if effective is much less than 2 to the n, then we have good news. Learning possible with infinite hypotheses. All right? So in this case, for example, we are seeing that effective number of hypotheses is less than the maximum possible hypothesis. Why do we care? Because if originally it is M is equal to 16, then effective number of hypotheses is equal to 14. So having these M to be limited, restricted, is good for us, because we want to minimize or want to have the probability of this bad event to be a small number. Okay, so that is one of the main goal of considering this effective number of hypotheses. Now let's give a formal name to the effective number of hypotheses that we discussed. Let's call them as dichotomies or mini-hypotheses. Okay, so we call them as dichotomy. So H of all points is equal to will be h of x1, x2, xn, which also means that the hypothesis, okay, or the dichotomy limited to the I of points or examples, right? So h of these all inputs will mean all dichotomies implemented by our hypothesis set on all points. So if you compare these hypotheses and then dichotomies, right? Hypothesis, all possible hypotheses and dichotomies, we see that in R2, they could correspond to all lines, and size could be possibly infinite. Okay, so possibly infinite this is. While dichotomy is upper bounded by 2 to the m. And then it's not the all lines, but the hypotheses that are grouped by kind. All right? So now we can call these dichotomies as a possible candidate for replacing our m in the Hofstein's inequality. So let me now introduce a so-called growth function. Okay, while dichotomies and effective number hypotheses depend on the inputs, so growth function removes dependency by taking the maximum of all possible labeling. So it is defined as the following: m of n. Okay, n is number of examples. So what this means is that the growth function measures the maximum number of ways these endpoints can be classified for a hypothesis class. Okay, we can think of this as the complexity of a hypothesis. For example, here, so again, lines in 2D, we have endpoints. The growth function measures how maximum number of ways these points can be classified. So maximum possible number of ways. For example, one point can be classified as plus or minus 1. Red cross or blue circle. 2 points can be classified as into 4 distinct labels, 4 different ways combination. 3 points to up to 8, 4 points 14. While considering lines, okay, when we talk about different hypotheses, this number can change. We are moving further from dichotomies or effective number of hypotheses into the growth function that will take an input given hypothesis and will give us a measure of maximum number of ways these points can be classified or labeled for this given hypothesis class. It is also upper bounded by 2 to the n, and importantly, it is finite. Let me introduce a definition called as a breakpoint of a hypothesis class. So if you take perceptrons or lines in 2D, what do we know about them? We have seen that perceptrons can deal with 3 inputs in providing all possible labels. It's sometimes called shattering. Okay? When it comes to 4 points, we will have 2 cases where perceptron will not be able to provide these specific kind of labels. This is called they're not able to shatter all points. I will go back to the previous slides to show this graphically. For example, here in slide 13, given 3 points, and perceptrons can provide all possible combinations of labels, all possible distinct labeling of these 3 points, right? You can provide all possible labels. So we can say that perceptrons can shatter 3 points. They can they can effectively classify all 3 points. However, in slide 15, I have shown you 4 points, and then perceptrons will have difficulty in providing these labels to specific cases. So perceptrons cannot shatter 4 points. They are limited. they're limited only to these labels. But in two specific cases, they are not able to provide these labels. So we have 14. Okay, if perceptrons or linear functions were able to shatter all these, we should have all 16 possible labels or label combinations. So if no k inputs can be shattered by h, in our example we talked perceptrons, they can be any different class of functions, linear, nonlinear, or different. We call k as a breakpoint for these class of functions or class of hypotheses. Okay, k a breakpoint. So the gross function is upper bound by 2 to the k. Okay, so k now is defining the breakpoint, not 2 to the n, but 2 to the k. We are further trying to minimize the m, or total number of hypotheses, okay, by taking into account this breakpoint. Okay, then k plus 1, k plus 2, 3, also called breakpoints. So perceptron cannot shatter 4 inputs, they cannot shatter 5 inputs, definitely, or 6 or 7 inputs. All right, so now important thing to note is that we need to find or use a minimum breakpoint of any hypothesis regarding the data set. Okay, and in perceptrons the breakpoint is 4. Why? Because perceptrons break at 4 points. They cannot provide these labels. We will utilize the breakpoint of a hypothesis when we talk about VC dimensions of a hypothesis class. For the time being, just remember what the definition of breakpoint and also the gross function. So far, we've been talking about the effective number of hypotheses, and we talked about the grouping by kind, and we talked about the gross function definition, with the hope that we want to find something, some good candidate to replace m. M is a total number of hypotheses that could be quite large. So this is, we call it as a some loose or bad bound. What we have here is probability that there exists a hypothesis in our hypothesis set that has the following bad event, okay, is upper bounded now with the following. 2 to the gross function m of m exponential. So moving fast forward, where I will put here the main results, okay, which is also called as Vapnik-Chervanenkis bound. So Vapnik and Chervanenkis have proved that when we have a large number of training examples, the probability of this bad event can be upper bounded by the following quantity. So the proof of this is again a few pages, but for our class it is sufficient to know the following main message of Vapnik-Chervanenkis. So VC in short, okay, is the following bound. It's based on further extension of the Hofstein's inequality, taking into account the breakpoint and the gross function of the hypothesis class. So probability of bad event is now upper bounded by 4 gross function to n exponential and the following quantity. The VC bound works for any hypothesis G selected by algorithm based on the data, using the data from our hypothesis set, given that we have large amount of data. Then the probability of bad event is upper bounded by the following inequality. So probability that there exists one hypothesis with the following bad event is upper bounded to 4m gross. This is the gross function and exponential. And if we have a breakpoint here, for example, for the given hypothesis that we are analyzing. It's even better. So the bound will be equal to the following: 4 to k to n k minus 1. Okay? And the exponential. So if you have large number of data, we will, and also we have, if there is a breakpoint, then the right hand side of this inequality will be small, or will exponentially decay. So we can summarize 3 points. First, it is important that, okay, growth function breaks at k. Then we can call this class of hypothesis good. So if growth function of this hypothesis breaks at k, it's good. Second, if you have large enough data, okay, it's good. Because if n is bigger, the right hand side, this will be smaller. And we can claim probably our hypothesis generalized to out of sample or target function out of sample error is equal to in sample error. And 3. So if algorithm picks a G with small in sample error, it's good algorithm. And we can see, we can hope that we probably learned. It's important to memorize, to learn, to remember this bound, as it is one of the key findings in theoretical machine learning research, which answers to the same question: if learning is possible or feasible, if we can guarantee somehow to approximate the target function which is unknown. VC dimension of hypothesis class, which we denote as dVC of H, is defined as follows: largest n for which the following hypothesis class and the growth function is equal to 2 to the n. Alright, so we can also say that the hypothesis that the most inputs, the hypothesis that can shatter. So perceptron had a breakpoint of 4 because perceptron cannot shatter 4 points. Alright, so the VC of perceptron will be minimum k minus 1. So perceptron had 4, breakpoint 4, minus 1 is 3. So VC dimension of perceptron is 3. So that means the growth function, okay, is equal to 2 to the 3. So largest n. So further, we can see that if n is less than VC dimension, amount of training data set, or the H can shatter some inputs. If k is greater than VC dimension, then k is a breakpoint for H. We can define this relationship. And further, if the number of examples or training points is equal or greater than 2 and VC dimension is equal or greater than 2, then growth function will be n to VC. Now how VC dimension is connected to learning. Now we are trying to characterize hypothesis class by its kind of complexity or power. For instance, so finite VC, if our hypothesis has finite VC, then G, selected G, will generalize. So generalization means that out of sample error and in sample error will approximate each other. And one important characteristics of VC dimension is that it works regardless of learning algorithm, regardless of input data distribution, regardless of target function, so these are great out. It only uses defines a hypothesis set and training example. Using the VC dimension of 2D perceptron, we can compare these two. Initially, we thought about linear separable data, and we said that perceptron learning algorithm can converge if number of iterations is large enough, which means in sample error is 0, right? And hopefully out of sample will be 0. But now, after doing all this analysis, it is sufficient for us to assume that the data is generated according to some unknown probability distribution, and y is generated by some target. Then the probability of this bad event, given that VC is 3 of perceptrons in 2D, and if we have enough large number of training examples, then we can say that out of sample and in sample error is approximate. What about general PLA in 3 dimensions or in higher dimensions with more than 2 features? What about their VC dimension? So we can still find the VC dimensions of a perceptron learning algorithm or any kind of other hypothesis generally. Another way to interpret VC dimension is to consider the hypothesis parameter, which creates some kind of degree of freedom. Okay, and also we can also relate it to hypothesis quantities akin to analog degree of freedom, or we can also relate VC dimension to the powerfulness of hypothesis. dVC is equal, in most cases, d plus 1. In perceptron case, d is dimensionality of our parameter space or data plus 1. So perceptron in 2D, 2 plus 1, 3, right? So hypothesis power. And also the analog degree of freedom. So we can relate VC dimension to number of tunable knobs in a radio, for example. So you can tune each, for instance, it corresponds to W or changeable parameter. Then we can relate the VC dimension to this number of knobs, 5 in this picture, for example. But generally, the VC dimension of a hypothesis represents the powerfulness of H. Okay? So higher the VC dimension, the more powerful your hypothesis class. That is the main, one of the main characteristics of a VC dimension. If we consider 2 examples here, positive phrase as our one example of hypothesis, right? So it's positive phrase. Then we have only one parameter that we can change to classify, for example, this one-dimensional input. Then the VC dimension of positive phrase is equal to 1. While positive intervals, this is our hypothesis class, then the VC dimension of these positive intervals will be equal to 2. Because one of the examples is that the free parameters. We have 2 parameters here to change L left and then right side, while here only one parameter. So practical rule of thumb is we can link the VC dimension to number of parameter your hypothesis class have, but it's not always the case. Okay, so I mentioned that VC dimension can represent how powerful your hypothesis class or the powerfulness of your H. And if your H hypothesis class have more free parameters, it is more powerful. More parameters means more tunability. Now let's talk about M and VC dimension. M is a number of hypotheses. And also, let's revisit our two central questions. First one was, can we make sure that out of sample is close to in sample error for this chosen G? Second, can we make sure in sample is small enough? We answered these two questions using the trade-off between M's, possible number of hypotheses, the size of hypothesis. When we said that small m leads to answer yes for the first question because the probability of bad event is small, because m is small here. And to the second question, can we make sure in sample area is small enough? No, because we have too few limited hypotheses, set of hypotheses. When m is large, we cannot make sure the out of sample area is close to n because the right hand side is big. Probability of bad event is big. Yes, we can make sure that in sample approach 0. Why? Because our hypothesis set consists of big number of hypotheses, right? So we have a lot of choices. So now let's try to answer the same question using the DVC or Vapnik-Chervonenkis dimension of a hypothesis class. So if we have a hypothesis with a small VC, we can make sure that out of sample and in sample is close. Why? Because probability of bad event is upper bounded by 4 times small VCs. This quantity will be small. Okay, this exponential. And the answer to the second question is no. We cannot make sure in sample small enough because we have very limited power, restricted power. How about large VC? So if you have a hypothesis with a large VC, can we make sure out of sample approximates in sample error? The first answer is no, because the P of bad will be big. VC is big for this hypothesis class. We got rid of M, but replaced with VC, right? VC, and also the growth function. So if we have a large VC, we can make sure that in sample will approximate to 0 because our hypothesis is powerful. Look, this is powerful, but while here we said many choices. So we're trying to represent the hypothesis class in terms of the VC dimension now. Okay, now the next question is using the right VC is important. But before we said using the right M is important. Let us now rephrase the VC bound to derive the term called penalty for model complexity. We said that VC bound works for any hypothesis regardless of algorithm, given that data set is large. And we said also probability of bad event is upper bound by the following VC bound. This is a bad event. This is, let's denote it as some delta. What would be the good event? So if we rephrase this, we can say with probability, okay, greater than 1 minus delta, which is we are making good event. The good event is the following case. So in sample is different from out of sample, less than or equal to epsilon, while here it is greater than epsilon. If you set delta to be the following term, we can solve for epsilon, right? So we do some simple rearrangement. Okay, this goes here, numerator and then exponential if we take the natural log of both sides, and then we can derive for epsilon, which will be equal to the following term. Now we can take this and replace it with the epsilon, right? Substitute. So what we have here. So let's call it as the difference between two as generalization error is upper bounded by the following quantity epsilon. And if we solve for the E out, then we'll have the following relationship. So E out now is upper bound by in sample error of the following given hypothesis G plus some term. We can call this term as a model complexity or penalty for model complexity term. The main VC message is described in the following slide. Okay, so we can say that with a high probability, out of sample error, which is unknown, is upper bounded by in sample error, which is known, which we can calculate or estimate, plus some model complexity term. Let's call it as omega of n, h, and delta. All right, so now h here corresponds to our hypothesis class, which in turn has its VC dimension parameter. N is amount of training examples, right? Delta is user-defined value, similar to tolerance. But we're interested in the interplay between VC dimension, DVC, and in-sample and out-of-sample error, assuming that we have sufficient amount of training data. So now let's take a look at this graph, which shows the error versus VC dimension for a set of hypotheses. So our goal is to minimize error in general, right? In sample or out of sample error. So as we can see, as the VC dimension of a hypothesis increases, the in sample error goes down. So we observe decreasing or exponentially decreasing in sample error. What about out of sample error? We see that if out of sample error or the hypothesis VC dimension increases, out of sample error also increase. This is something that we want to avoid. We also have one graph here shown which represents model complexity. All right, our goal is again to make sure that out of sample and in sample error remain close to each other. All right, that is a bad event. We don't want them to deviate. All right, so there will be one point with the proper VC dimension that the difference between two out of sample error, in sample error will be small, okay, given that the in sample is small and they start to deviate. So we need to find a hypothesis with the proper VC dimension. While here the 2 is different, I mean less different between out of sample and in sample. However, the error value is too high. So we can conclude that if you increase VC dimension of hypothesis, or if you use hypothesis with a big VC dimension, then in sample will be 0. However, out of sample error will be big because in sample plus model complexity. So model complexity will go up because VC is high, right? This term goes. Well, if we use small VC, then model complexity will be small. However, in sample will be higher. So together will lead to a big out of sample error, right? Now our task is to find the best combination of VC dimension and number of training examples so that in sample plus this complexity term remains minimum. Now why VC? If VC is small, in sample goes up because we related VC as the powerfulness of the hypothesis, right? The small VC means our hypothesis is too limited, too restricted, so the error in sample error will be big. While if you use too powerful hypothesis, then in sample will approach 0. So we need to find, okay, the hypothesis that is proper, so that the out of sample error will be small, right? So powerful hypothesis is not always good. Can we use VC bound to identify the sufficient amount of training examples or data in order to make this right hand side small? This problem is also called as sample complexity. how large data set I should have. So let's first fix the following parameters: epsilon 0.1, delta 0.1, and let's assume that the VC dimension of our hypothesis is 3. And as a result, we want the following. So we want this to be equal to 0.1 or smaller than that. Next, we can, once these parameters have been set, VC dimension, epsilon, we can try to use datasets with different number of training examples. Here, for instance, we can try 100 examples and calculate the bound. You just plug in the bound and then calculate this one, or 1,000, 10,000, 100, or 29,000. As you can see that if we increase number of training examples, eventually we get decrease in the bound. And when we have 100,000 example for a hypothesis with a VC dimension 3, and this is our tolerance rate, then we will have a very small number. While the expected one that we wanted is achieved with 29,300 examples, if this is this. So we set this delta. What is delta? So delta is 0.1. We can tolerate this. So probability of this being different, let it be like 0.1, which is not that bad. If this is our expectation, then we need to use 29,300. So the VC bound can also be used to identify the sample complexity, how many training examples we need. Usually, this is the, in theory, we need the n to be 10,000 times the VC. For example, here, if we have 3 times 10,000 is almost 30,000 examples in theory. But in practice, 10 times dV should be enough. If we are using hypothesis with 3 VC dimension equal to 3, then you should think of using at least 30 examples so that the probability of bad event, this will be small. Let's take another interesting example. Consider the VC bound given below. The question is, how can we decrease the probability of getting bad data? First, shall we decrease the model complexity, increase data size, increase generalization, error tolerance, or all of the above? So the correct answer is here. So all of the above choices will decrease the probability of getting the bad data. Let's summarize this lecture. So first, we introduced two central questions which stated, can we make sure out of sample error approximates in sample error, or vice versa? And second question consists of the following: can we make sure in sample error is small, approximates 0? And then we ask the relationship of M, the total number of hypotheses, in answering these two questions, right? And we introduce effective number of lines or hypotheses, which we have seen through the eye of inputs. So effective number of lines or hypotheses were grouped by kind. And later we introduced a so-called a growth function, and the breakpoint. And also we have introduced the definition of the VC dimension and interpretation of it, right? So VC dimension plays a very important role in model selection, or in generally in machine learning, and as it can easily be used to characterize model complexity in most cases, but also can be used to define sample complexity. So knowing VC dimension is very important part of this lecture series.